Good morning, dear students. Welcome to this session on pre-stressed concrete. We are talking about Unit 2. So let us see. We are talking about stresses in tendons. Uh, so last session we have discussed about the need for finding stresses in tendons. Though you are getting a ready-made value readily available by in the digital form or maybe the analog form, whatever it is, but still due to the pre-stress inducing into the concrete, there will be hogging bending to the member that will create additional strain in steel, and also the loads will create some additional strain, sagging in the steel. So the net deformation of the member is going to have the strain, additional strain in the tendon that will create the additional stress in tendons. Okay, so this is what is calculated, and we have now proved that the uh, within the elastic limit of the steel, if the stress is stressed, the tendon is stressed, then there won't be much change in the stress, okay, in the steel, right? Now let us talk about the bonding nature between steel and concrete, how it is going to affect the stress in steel. Okay, there are two such cases. We have bonded and unbonded tendons. So this is being discussed already. What is a bonded tendon and what is an unbonded tendon? Okay. The rate of increase of stress in the tendons of a pre-stressed concrete under the loads depends on the degree of bond between high tensile steel and the surrounding concrete. Okay, so if the bond is more, the increase in stress increase in tendons will be more, right? So if you take a bonded member like pre-tensioned or post-tensioned grouted, these two are the examples for bonded pre-stressed member. Okay, so stress in steel is computed using composite action up to cracking. Once cracking is induced, then it behaves like an unbonded member, right? Next, when you take unbonded members, the example is post-tensioned member. Stress in steel depends on average strain in concrete at the level of steel. Okay, so this is how we calculate the additional stress in steel or change in stress in steel uh, because of these variations from the bending natures uh, which arise due to pre-stressing and also the loads. So bonded members, uh, if you want to calculate the stress in steel, you have to use composite action. For unbonded members, you have to calculate by or with the help of strain in concrete at the level of steel. Okay, right. Let us first start with bonded tendons. How we calculate this stress in steel for a bonded tendon. Okay, right. Uh, Capital M, moment at the section due to the loads. Young's modulus of steel and Young's modulus of concrete. Y means the position of steel from the centroidal axis. I mean, if the cross section of the member is like this, so this is the CG of the cross section. Okay. For example, if the tendon is placed somewhere here, okay. So this distance, what we call is Y. Okay. Right. Position of steel from the centroidal axis. Right. F is the stress in concrete at the level Y from the centroidal axis. Means at the level of steel. Stress in concrete. F means stress in concrete at the level of steel. So at this level, what is the stress value in concrete? That is F. I is the second moment of area or moment of inertia of the section given, and alpha is the modular ratio. Nothing but and it is also being denoted by M, or else some textbooks say, okay, modular ratio. So here it is mentioned as alpha. So Young's modulus of steel divided by Young's modulus of concrete is known as modular ratio. So 1 by M is the notation used in the other textbooks, or else conventional concrete, for conventional concrete. In case of RCC designs, we will be using 1 by M as modular ratio. Here it is mentioned as alpha. Okay. Right. So bonded tendons, if you take, so there will be bond between steel and concrete. Hence, if you want stress in steel, it is like a composite action, as already we told that. So you know how to deal with composite section. A concrete may be converted into equivalent steel, or steel may be converted into equivalent concrete. So this concept is already there for you in strength of materials, right? So using that composite action, the stress in steel is calculated just by multiplying the modular ratio with stress in concrete at the level of steel. That's all. Okay. So what you need is, say for example, you have a concrete member. Okay. So having, say for example, the CG somewhere here, and you have the tendon placed at this location. So this is the location of tendon. So plot the resultant stress diagram from the regular analysis. So for example, imagine this is the stress diagram. Say somewhere 10 or some 6 megapascal is the value. So now what you do, just find the stress in concrete at this level. What is the value of stress at this level? Okay, got it. So multiply that stress with modular ratio, that will be converted to stress in steel. So this is what is called composite action, utilization of the concept of composite action. Okay, right. So this is what we call Y. Okay. So the stress in concrete at the level of steel is M by I into Y. So we have the bending formula. M by I is F by Y, right? Or sigma by Y, whatever notation you use. So in M into Y by I is F. Okay. So this is how we will be able to find the stress in steel if you have a bonded tendon. Okay, right. So it's so simple. Find the stress in concrete at wherever the steel is there, at the level of steel. Once you find the stress value, this F value, by My by I, simple bending formula, multiply that with the modular ratio, nothing but ES by EC, Young's modulus of steel divided by Young's modulus of concrete. Okay, right. So now going for how to deal with unbonded tendons, where there won't be any bond between steel and concrete. Okay, post-tensioned pre-stressed member, we leave a duct. We put a pipe-like thing, duct. Okay, so in that duct, we will insert the tendon. So there won't be any no bond between the steel and concrete, right? Steel can move freely. Okay, there won't be any gripping action from the concrete. Right. In that case, how you find this composite action is only possible when there is a bond or gripping action, a bond between the two materials, right? If that is not there, so that shall be treated in the other way, right? So taking delta L as total elongation of the cable at a distance y from centroidal axis, total elongation of the cable wherever it is at a distance of y. Total length of the cable is taken as L, and M is the bending moment at that section. Okay. So now strain in concrete at the level of steel. What is a strain in concrete at that level? Okay. So it is like stress by strain F divided by strain in concrete is equal to stress by strain is equal to Young's modulus of concrete, right? EC. So what you want is strain in concrete you want. So it is F by EC. What is F? M Y by I divided by EC. Okay, so F divided by EC is equal to strain in concrete. So what is F? Substitute for F, M Y by I. So that is this expression. Now this is for an element for a length of now some dx. If you take an element of length dx, okay, a total elongation of the fiber of concrete at the level of steel. So you are finding just at this level. Okay, if you just adjacent to that, if you can pick up an imaginary line of concrete, okay, so how that is elongating, right? That will be related to steel, okay, because we have strain compatibility. So though they are unbonded, but the both the fiber of steel and the fiber of concrete shall have strain compatibility, means shall have same strain. So that is being utilized here. So the total elongation is nothing but the integration from 0 to L. So for a length of now, if this is a beam of L, so what you have considered is only a dx portion. So if you want such a strain in concrete for total strain for total length, that is strain for dx length. Okay, strain mean change in length by original length for a length of dx. If you want it for total span, you have to integrate from 0 to L. Okay, right? So dx is the elemental length. Okay, now what happens? Delta L by L, that is average strain. So divide this expression by L, 1 by L. So take out all the constant terms outside. Okay, right? So Y is constant because the distance from centroid throughout the beam it is same. Y is same, EC is same, I is same, L is same. Okay. Only bending moment. Okay. You see Y is constant. Y in the sense the distance of the layer of concrete at the level of steel from CG is same throughout this, you know, length of the beam. Y is same. Okay. Young's modulus of concrete is constant and the moment of inertia is constant because cross section is not changing. Okay. And only bending moment is going to change if, say, for if you take UDL, bending moment is zero at the support, maximum at center, and it's parabolically varying. Okay, in between. So that is m is a variable. So keeping m inside, bringing all other terms outside. So y by e I l divided by l, average strain, change in length by original length, right? So stress in steel, if you want, this is strain in no, concrete. Okay, nothing but the similar strain is possible in steel also. So stress in steel, if you want, uh, Young's modulus of steel multiplied by the strain. Okay, so now we got the strain value of concrete that is equal to strain in steel, because as I told you, strain compatibility shall be there. So stress in steel divided by strain in steel is equal to Young's modulus of steel. So now you want this stress in steel and you know strain in steel from this formula and Young's modulus of steel. So what happens? Es into small es. So es into this term has come here. 1 by EC y by IL integral m dx. So what is Es by EC? Modular ratio alpha. Alpha into y divided by I into L integral 0 to L m into dx. M is variable, right? Okay, now integral m dx is 0 to L. M into dx is nothing but area of bending moment diagram, right? M into dx. Okay, for that element. So if you do such additions, so for example, you take BMD for UDL is a parabola, right? So if you take dx length, this is dx length along the beam, okay, and this is m value. So m into dx is area of this strip, right? So if you take all such strips of dx lengths from 0 to L, it is nothing but integration. So what you get is the total area of BMD. That is what is this one. So capital A, area of BMD. Okay, so this is area of BMD. So alpha Y A by IL is the stress in steel for unbonded tendon. What is capital A means? Area of BMD. What is Y means? It is the distance of the location of steel from CG of concrete. Okay. Alpha modular ratio, alpha suffix uh, E it is, okay, equivalent in the sense, something like that. Capital I moment of inertia, L is the span of the beam. Okay, so this is how we are able to find it. Now just a standard case where it's very common case what we get is UDL. So if it is there, a UDL is there on the member, then what will be the area of BMD is like 2/3 of base into height. Okay, so 2/3 of Base means length L. This is what is L. Height is WL square by 8, right? What is maximum bending moment? WL square by 8. So just L into WD L square by 8. 2/3 base into height. Okay, that is what is written here. 2/3 base height. So what are you getting? WL cube by 12 finally. So that if you substitute here for capital A, so what are you getting for a UDL case? Alpha y WL square by 12I. Okay, yes, L cube is there, denominator L is there, so L cube is there in capital A, so one L goes and L square remains. Okay, so alpha y, alpha suffix e y w L square by 12 I is the formula for finding increase of stress in steel. Okay, right. So the rate of increase of stress is larger in case of bonded beams than unbonded beams, both in pre-cracking and post-cracking stages. This will be seen no, upon seeing the research results presentation. We have a diagram. We can see that how the bonded and unbonded beams are behaving uh, when you load it pre-cracking and post-cracking stages. Okay, so once you load it, the member is going to take the load and you go on increase the load, cracking starts. So once the cracking starts, so that will be called as post-cracking stage, and the rest of the thing is like pre-cracking stage. Okay, so that is how it is. So bonded beams are preferable due to their higher flexural strength and predictable deformation characteristics. Okay, so this is how it is going to be, right? So we will discuss the rest of the things in the next class with an example also that completes that the uh, stresses in tendons topic. Okay, that we will take up in the next class for the rest of the content. Okay, thank you.